Ah. Where did we get it?
We took it last year. No, that's Carlo. Yeah, he does not have a nice photo anywhere.
Who is this? Carlo?
Yeah. Last year, we were in Salamanca for this conference, and Barbara had a talk in about this, about some of the work Rosenwald Porter model that they were working on with Carlo, and she wanted a photo of Carlo, but he didn't have one. So we were visiting, touring the city, and we took this photo. Oh, welcome. It's not like that.
President.
Oleg,
Yeah.
the old seminar master is here.
Yeah. Do you want to discuss? Oh, we don't have any participants.
I will take this.
This is also for you.
Is Aniket here?
No. It's not the second shifter, so we need to wait.
I woke him up in morning at 10 because he asked me to.
But then what happened?
I don't know. I came here.
And apparently he didn't.
Yes.
Hey, good afternoon, PCS members and friends. Today we have a scientific seminar about Dr. Rohit Kishan Ray, and our scientific host today is Professor Sergey Flach. Sergey, please introduce our speaker.
Yeah, welcome everyone. So it's a pleasure to have Rohit with us again. For those of you who don't know him, just a brief CV. He did his undergrad studies in Kolkata at the University of Kolkata, and then he did his Master of Science at Jawaharlal Nehru University in New Delhi. And then he moved on to finish his PhD in 2023 at the Indian Institute of Technology in Kharagpur. And then he moved to Korea and was with us for, I think, roughly 2 years until this year, early this year, I think. And when he moved to Virginia Tech, where he is now a postdoc associate, and he is now on a relatively brief visit back with us to finish a project. And I think, thank you, you agreed also to change your talk title.
Yes.
And talk about this project.
Yeah.
So let's welcome the speaker.
Thank you very much. Like Sergey already thanked me for, so this is not the advertised talk in case you are here for classicality, witness, and all those things. You have to wait for some other talk. So this is a work that is the work that I started while I was a postdoc here. And because of timing and other issues, finally we have finished the work, and it was finished, I think, yesterday or something like that. It was very fresh. And those of you who cannot recognize this person, this is Carlo Danieli. And
where is this picture taken?
This picture was taken at Salamanca last year. And this is obviously Alexei and Sergey. So I hope this works. No, just
to click one time and probably it will work.
It slips. So Basically, just to give you a brief overview, I am going to talk about flat bands with broken time reversal symmetry and spatially compact currents. And I will first give you an overview of what time reversal symmetry is, and in our case, then I'll talk about all bands flat model, then ABF, and then I'll talk about how we are using ABF constructions with flux. Flux is here the magnetic flux, which will break the time reversal symmetry, as we'll see, and then I'll show the construction of ABF in higher dimensions. So basically, this will be like one-dimensional case. Then I'll show what are the localized currents and how they are formed. Then I talk about general flatband cases, and then I'll summarize the result. So time reversal symmetry. So T here is an anti-unitary operator, and we say that the Hamiltonian has time reversal symmetry when it is invariant under this transformation. And so to break the time reversal symmetry, it's basically this equality has to turn into inequality, non-equality. And the typical form of this time reversal operator is an unitary with a complex conjugate operator K. For spinless cases, this time reversal operator is basically complex conjugation. So any unitary operation on a given Hamiltonian which has time reversal symmetry may not preserve time reversal symmetry. So a necessary and sufficient condition for the TRS, the time reversal symmetry, to hold is this condition, that the unitary that is being used is also time reversal symmetric. And it can be shown that so if this equality does not hold, then what happens? Then we can say that that unitary operation may break time reversal symmetry. So the thing is, suppose you start with a Hamiltonian which does not have time reversal, which has broken time reversal symmetry, then you need to be really careful about which unitary operations you are using so that we do not gain time reversal symmetry or something like that. So one of the safest options for our cases, so which is a spinless case, is take orthogonal unitaries with real entries, and that preserves the time reversal symmetry nature. So if the time reversal symmetry is broken, then it remains broken. And if it is not, then very good. And suppose that is not the case, you have some general kind of unitary, then this condition needs to be maintained. And then you can show that the time reversal symmetry property does not change under that operation. I am going to talk about cases where we define Hamiltonian lattices of this form, where we have the unit cell defining matrix, and we have these hopping matrices, and S is the order of neighborhood. So S equals to 1 is nearest neighbor, S equals to 2 is next to nearest neighbor, and so on. And J here is the dimension index. So J, if J is 1, basically it's one dimensional. J can have 1 and 2 or X and Y, then it will be X and Y, and so on and so forth. So all band, so before just a small recapitulation of all bands flat model, and especially I will talk about this construction method that Alexei and Sergey and Carlo and others have developed, which is something to take a kind of semi-detangled kind of setup and apply local unitaries, and then get a non-detangled set, a non-detangled lattice. And because the unitaries do not change the spectral property, so in the semi-detangled case, like we can see that suppose in this case, like there are 5 bands, and because this unitary transformation does not change the spectral property, so the eigenvalues in the bands remain flat in this case. So this is all bands are flat here, and they remain so, and that is the basic trick. So if you just start from here, then one has to find the particular weights on these bonds so that there is destructive interference, and you can have compact localized states, and you can have all bands flat. But instead, if you start from here, then it's a very clever way to generate a network like this. And this is the basic construction that we'll use. And all band flats basically imply that the compact localized states, they are orthogonal. And in this case, detangling and entangling is possible, which is this unitary operation. So it can go this way and it can go the other way as well. And the only thing about these local unitary operations is that they commute. So this is the basic framework on which most of the talk will be involved. So just to talk about another thing, a naive idea could be that if we have like complex hoppings on these bonds, then basically these these Hamiltonians, that Hamiltonian that defines this network or lattice becomes has broken time reversal symmetry, and this network that generates from this in this case, if we use orthogonal unitaries, then that will also have broken time reversal symmetry. But we'll see later on that it's not very interesting.
So can I ask you
Yes.
something? I'm still thinking about it. Why you need two unitaries? Why you don't just take one? Because if you take a product of UX, UI, probably
Yeah, you can.
it will also work.
Sure.
And then the question is why you need them to commute?
So I need them to commute because the order should not matter. I'm defining it this way, that I am, say, you have this array of semi-detangled lattices, and then what I'm thinking is, what if I just entangle along this direction?
But the question is, can you think about this? You just entangle something in a clever way with one operation?
Yeah, you can.
But then what?
If you have UX UI product, a
Yeah.
general U, if they are commuting, then it does not matter whether it is UX UI or UI UX.
Yeah.
Right.
But
So
is this just some sub set of operations? You can
Yes,
do?
yes. In this case, I am using this thing. You can use a general U, and you can entangle as whatever way you want, and the same principle will follow, but it may not look nice.
Okay. You want something nice. Okay.
Yes.
That's
Whatever we'll do, we'll try to make things look nice.
That's an answer to my question. Yes.
Yeah. So, like I was saying, that just putting a complex hopping on any of the bonds and then breaking time reversal symmetry can give us the desired all band flat kind of structure with broken time reversal symmetry, but it may not be interesting enough. And by interesting enough, I mean that we may not have these spatially compact current kind of scenarios. So what we start with threading a flux through a loop. So here you can see that there are no loops. So these are basically standard process. But what if I replace this center part with, say, a loop, a polygon? And if I do, what is the minimum size of that polygon, which is a triangle? And if we start from there, then basically we have these triangles. We set them in a 1D array like this. And these are the local unitary operations. This is where we operate with the operation. And then it can be shown that if you have this kind of unitary, which is orthogonal, then you end up with a network like this. Now, the problem with this is that we had, previously, we did not have any intercell hopping. So we had only a 0 terms. Now we have not only intercell hopping, but we also have next to next nearest neighbor hopping also. The matrices look something like this. So this is the post-operation matrix, and this is the first case. So, like I said in answer to Oleg's question, that the objective is also to make things look nice. To make things look nice, we can increase the number of bands. So instead of just considering a simple triangle, we can add these appendices and we can entangle those appendices only using the same unitary operation. And if we do that, then we get this pretty nice kind of structure. And then basically, because we have traded flux in this polygon, which is enclosed, and the CLS basically has amplitude on all the sides, so it basically gives us localized currents, and it can be extended to any kind of polygons. And for example, you can start with like a kite rhombus kind of structure, and we have just aligned it in such a way so that the end product looks nice. So as you can see that there are these extra appendices, this can be used to stack and expand this in the 2D plane as well. So this is another example where instead of now, so we start thinking about how do we tile similar structure and how do we span the 2D plane. And one of the ways could be like we start with the same triangle kind of setup, because we are now going in both the directions. So we add an extra appendix, it becomes a 6-band kind of structure. But the funny thing is that it can be stacked on top of each other. So we have this, and we have another one like this. And this entire 12-band unit cell can then be used to create a network like this. And basically, we are having this is the location where we are applying the local unitary operations. If you do not want to do that, say that let's not increase the number of bands, try to keep it minimal, then we can have something like this. But there is a difference. The difference lies here. In this case, all the operations are SU2 unitary. So why? Because we are only entangling between two sides. So we are kept things simple in the sense that the operation is not very complicated.
But you told us that you use orthogonal matrices, not unitary matrices to entangle.
Orthogonals, unitaries are orthogonals.
Yeah, I understand, but just SU2, it's like a broader class.
Yes, I know.
Yeah, I'm just asking because maybe something.
No, so like I said that if you remember this side.
Yeah, cosines.
Here, if they are not orthogonal, then this criteria needs to be satisfied, which can be used for unitaries. So that is why I'm using unitary. Yeah. So the difference between these two types of tiling is, in this case, the number of bands go up, but the unitary operation can be taken from a simpler group. But when you try to minimize the number of bands, basically then in that case, it's entangling between three sides. So now we are having rotation between we are taking rotations from SU3. And this is just one example. It could be any other matrix. So now I will talk about this particular structure. And it's very simpler in the sense that I have now so to answer your point, like, as you can see that here, I am not saying that I am using UX or UI.
Yeah, right.
But here I am going to do.
Okay.
So to make things simpler. So all this red purplish kind of is the Y direction unitaries that I'm using UI, and the green ones are the UX. And I've started with this 8-band kind of structure where I have this polygon inside and all these appendices. And this basically, another reasons of using the appendices is that it gives us an intuitive way to expand. So you just entangle the appendices that are in a particular direction. So for example, if you want to entangle in this direction, then you just select these two appendices. If you want to entangle in the Y direction, then you select these two appendices. So you get like an intuitive way of tiling the entire 2D plane. And we'll see later the 3D also. So after this unitary operation is done, this is what we can get. The green sides are basically denoting the CLS, which now shares with like 4 neighboring unit cells. And the circulations are still within, and I'll show later what the values of the circulations are and how they look in this case at least. And just like I was saying, that if we want to extend the same structure for 3D, we can be a little bit creative, and we can consider, say, the tetrahedron structure, and then we can add the appendices, because we learned from our previous experience, if we don't add the appendices, then it becomes messy. And in this case, for example, this 8-band can be tiled in this way, so like a pyramid kind of structure, and you have SU4, you select your elements, rotational elements from SU4 group, because there are 4 sides which come close, come together, and that's how you can tile. Or you can choose to try to reduce this SU4 to some lower order group, and to do that, we can take a hint from our previous design, and we can put one tetrahedron on top of another. But the thing is that in that case, you get an ensemble, like 2 different kind of unitaries you have to select. So these are obviously SU2. They complete this, but here and all these 3 sides, they come together from all over the place, and we get basically 8 sides which come together. You can do similar thing, but say you take a hexahedron, it's the same thing, but hexahedron being quite symmetric. In this case, basically you get 16-band, and all of these are basically SU8 unitaries. It looks messy in the sense that I wanted to emphasize that the appendices which are coming together, but if you stack them close, basically it looks nice. So coming to the localized currents. So I'm computing basically probability current, which is given by this standard equation. And it's basically 2 different unit cells, which indices M and M prime, and mu and eta are basically site indices. So if M and M prime are basically the same thing, then this H matrix is basically unit cell matrix. And if they are, say, different, so this H could be depending on whether they are nearest neighbor or next to next nearest neighbor, H could be taken from that case. So in this case, this is the unit cell matrix, and these are the hopping amplitudes, which basically represent like a phi flux that is being threaded through this. And this is the post-unitary operation hopping amplitude that we get from the appendices. And because the CLS, because there are 8 bands, so basically the 8 eigenvectors, this is the transformed eigenvectors. If you see prime, that means it is post-unitary operation. But it doesn't matter, because the unitary operation does not change the overall current value. So it's kind of like gauge invariant in that case. So this is the current profile that you can get, which you can see that it's directly related to phi. And in fact, the values where the hopping amplitude, the values of phi for which the hopping amplitudes become real, we get that the currents are also 0 over there. So for example, minus pi, and 0, you get real hopping amplitudes, and the current goes to 0. And other than that, it's all good and nice. This is a numerical result for this thing, and it's for phi equals to 2 value. So that's it. And basically, in this case, at least we can see that the current remains localized within the original placket where the flux was threaded. In fact, all the other plackets where the flux was not threaded, but we got the placket because of the unitary operation and all those things, the current does not exist, and that is why it's localized. So what about general flat band cases? So far it was orthogonal CLS and all band flats. But what about the situation when all bands are not flat? So we can do.
May I ask?
Yeah.
One question. Here, is the local unitary operation plays the time reversal symmetry?
It does not.
Does not.
No.
You mean this the flux?
The flux that's breaking the time reversal symmetry.
No, but the question then is what breaks the time reversal symmetry?
If I understand correctly, this the transformation includes the flux information, no?
No. The transformation does not include the flux information.
Okay, then the Hamiltonian has.
The Hamiltonian has the flux information.
So the time reversal symmetry is broken already before you apply the unitaries.
I see.
The unitaries we are choosing such a way.
No, again, I mean the time he wonders where's the flux coming from. The answer is it's already put into the Hamiltonian before you start even applying this.
So let's look at here. Suppose there are no flux. So phi is 0.
Yes.
Right. Then this Hamiltonian does not have broken time reversal symmetry. It's time reversal symmetric.
I see.
But because of the existence of the flux, this complex hoppings that we are putting, time reversal symmetry is broken.
I see. This phi represents this the flux, and the theta
Is the parameter for, we call it rotation, but it's
not related with the flux.
No.
I see.
Yeah.
Can you change the flux by considering the complex?
You can change the flux.
You can change.
Yeah. In fact, this is by changing the flux. Phi is the flux that is being threaded.
No, but that's not the question. What did you ask again?
So you consider the real orthogonal transformation.
You mean
Yes.
unitaries?
You consider the unitary transformation. Can you change the flux of the system by justify the transformation? Just from the transformation. So you start from the low flux model and then transform it to a flux. Yes, flux model.
You can, in principle, because like I said at the very beginning, that any unitary operation does not preserve the time reversal symmetry, right? So similarly, if you start with a Hamiltonian, which is time reversal symmetric, you can start with any random complex unitary, which does not need to necessarily satisfy all the conditions that I outlined before. And it can, in principle, change the Hamiltonian to a non-time reversal symmetric Hamiltonian. So that can happen. That's why we are trying to be a little bit careful with what unitaries we choose. And to be on the safe side, we are choosing just the orthogonal ones.
So the one
Yes.
so the question, second question about this, the form of the currents that you use the here the vector potential included in this expression.
It can be, because if we look at this expression,
Yes.
then it can be, depending on what you are defining the current with. When I'm talking about current, I'm talking about probability current.
Probability current.
Yes. But you can have charge current.
I see.
The equation will be kind of similar, but then the vector potential will come in through this Hamiltonian or some other part.
I thought that simply you multiply the charge to this, the probability current makes this.
I think it's the same thing. Probability or charge is the same thing.
Could be.
Okay. In this the system, there's a flux and the vector potential is finite, and
But you see, you don't have to, when you think about vector potential, you think about magnetic fields, right?
Yes.
Yeah. So, but maybe there is no magnetic field.
No magnetic field.
Let's say there is no magnetic field. We don't know what a magnetic field is. We just have complex hoppings,
Mhm.
which
But I mean, you
generate
can use-
currents.
You can use pure substitution.
It's relevant.
No, again, when you write down the model, it's not. I mean, if you want to realize the model in real life, let's say using a magnetic field, then yes, then you have to think about.
Yeah, you are integrating over the vector potential and you are getting phi at the end of the day. I'm just talking about the phi.
But even then, Misha, there are also lots of artificial, how is it called?
Synthetic magnetic.
Synthetic magnetic fields, which has nothing to do with the magnetic field, and yet people even do some experiments with AC driving and such things.
Yes,
Blockade systems.
yeah, but the simplest way to produce
Yes.
flux.
But again, you don't have to start from a magnetic, because okay, you can just start from complex hoppings.
Yeah, you cannot say you put vector potential and phase.
Yeah,
This is too
Yeah.
too
I didn't.
too much.
You didn't say that, right?
Yes.
So
One
I think one of the reasons of what Rohit is calling nice looking structures, especially in 1 and 2D, is probably that maybe you can try to realize them using magnetic fields and charged particles, if you wish so. And then you can of course ask what is the vector potential and so on and so forth. But you don't have to.
But then it will be very hard to have local magnetic field only here, but not in the neighboring unit cell.
Yes, but again, I mean, there is all this stuff about these synthetic magnetic field, which people realize with totally different means, without magnetic.
Yeah, of course you can have optical lattice with some even polarity on some complex hoppings. So yeah.
in fact, I think last year
Even
or the
without
year
any-
before that, they were creating this pseudo magnetic field kind of stuff, which was coming from some spin orbit coupling. They were not actually putting a magnetic field.
Spin orbit coupling usually doesn't violate time reversal symmetry.
No, they were creating that, they were defining that coupling, and they were calling that the internal magnetic field or something. And then they were using it to show that TRS can be broken. I'll send you the paper. It's an interesting work.
I have another question. If you apply some kind of unitary transformation, all time you have new lattice. This lattice is still periodic, or you can imagine Ux and Uy to produce quasi-crystal or something.
Yeah, you can do that. You can apply random unitaries in space.
Yeah.
And then you get a new Hamiltonian.
Because in
it's
this-
random, but actually it's not, right?
Right, it's still
Right.
some kind of
Yeah.
correlations and
Yeah.
beautiful flat.
But you can do this with any, I mean, look, take a 1D tight binding chain, which is position invariant, and apply local unitaries which are random on the lattice. You will get some random looking Hamiltonian, but actually still the good old tight binding chain. So there are many ways to look at the same problem in some high-dimensional physics space.
But really quasi-crystal is
Also, why not?
I mean, if you just look at the end product.
because I see
Yeah.
this some plaquette and possible
Yeah, I mean,
different types.
the thing is like, say you are applying the unitaries in this direction and so on. I have to make sure that I am applying an unitary. If I'm trying to maintain periodic boundary condition, I'm applying the same kind of thing that connects this to that. But if I don't, that's a choice. And then I get this open boundary kind of thing. I have tried to, like, we have tried to keep it as simple as possible, and we see what we get from there. If we did not get all this interesting stuff, maybe we would have added something more. So an example of adding something more in this case. So we have this triangle setup from our previous ABF design, and we basically introduce these connected sides, and this gives us not all bent flat kind of scenarios. And then we apply, say, this kind of local unitaries. And if we do that, again, we get all kind of hoppings. So literally taking a leaf from our previous design, we can just use an appendix and then just connect. And this gives us another setup where we have orthogonal CLS. At the same time, the current remains localized here. And it looks nice. What about, yes?
Can you make that one all bent flat? Because it looks like Rohit's lattice with just the dongle triangles.
Yes. So making it all bent flat, I mean, this part, there is this dispersive part, right?
Oh.
Because this part was already there.
Yeah, so you cannot.
I mean, not from this.
But that's more complicated, more bends.
Yeah.
You don't have just 2 bends, more 5.
Yeah, it has like
5.
4 from here and 1 from here. So 4 are basically flat and 1 is dispersive. So what about chiral flat bands? What about those cases? So consider this diamond lattice and consider like you put complex hoppings on this. What we can show that, what can be shown that the general CLS resides like on these sides. And I am marking green by the positions where the CLS have non-zero amplitude. So this is basically 0 amplitude. And because this is 0 amplitude, this is 0 amplitude. If you define a placket like this, in this loop, current becomes 0. Trivially. Because current requires 2 amplitudes and the hopping. So each one of the amplitude is 0, then basically current is trivially 0. So yes, you still break time reversal symmetry, but just like my first example where we had this cross kind of structure, if you do not have an already encircled situation, then you are not going to get current. TRS breaking is fine.
But that only is true because you still you have a chiral model, but you also have a basis which is the bipartite basis.
Yes. Yes.
Because you could again transform that using some unitaries
Yes.
into a basis which is not bipartite, but the model will be still chiral.
Yes.
And maybe then you will get currents.
No.
Why? How do you know? Because the argument doesn't work anymore. Because once you don't have a bipartite lattice, you cannot argue your CLS lives only on the majority.
Yeah.
So by definition, there cannot be any.
Yeah, but
by exciting one CLS, you cannot get a ring current.
Yes.
Right. But if I now transform away from the bipartite basis,
So
then
I can
maybe-
say from one experience, we had considered one of the first structures that I showed, which was chiral in that basis. Then we did unitary transformation, and we had the CLS which had non-zero amplitude on all the sides, and we could define the placket, but the CLS amplitudes were such that in each of the plackets, the current was still 0.
but why is that? No, but so I'm just saying that that's not so obvious for me. Why that?
I think that when we apply this kind of unitaries, we are computing basically probability currents. This acts like a gauge invariant kind of method. So if there does not exist a current before, then the unitaries do not generate a new current, and the unitaries of the kind that preserves the time reversal symmetry property.
I don't think so, because I can take your previous. You started the presentation with this choosing the so-called semi-detangled
Yeah.
case of an all-band flat
Yes.
problem, right?
Yes.
So then you have these molecules, basically.
Yeah.
And you say, okay, let them break time reversal symmetry and let me have a current in them. Yes, yeah. Good. But now I can actually do another unitary and diagonalize those guys. It's just another local unitary.
Yeah.
And as a result, I will get zero currents because now my
So the
states
question
all
is,
become
so the question is where you are applying the unitaries to?
to your model.
No.
All I'm saying is if I take this model
Yeah.
and I'm right now operating in a bipartite basis, and the flatband is protected, is a chiral flatband, and therefore whatever broken time versus symmetry I have, I cannot have currents. That's clear.
Yeah.
Which are sitting on one CLS. That is
Yes.
clear. But what I'm trying to say is that if I now transform away from this bipartite basis into any other basis which still will preserve chirality, then maybe my CLS will also somehow now live on all kinds of sides. There is no notion of majority and
I understand.
minority, so and then maybe I will have a current.
Yeah, so that is why I said that from one experience.
One example, you don't see this, but
Yes.
you don't know.
Yes.
Sorry, the question that about this wording chiral. Does it mean that the hopping is chiral or the phase acquired during the hopping is chiral?
Okay, what means chiral?
In which sense do you use this?
I'm calling it chiral in the sense that there's majority and minority kind of sublattice structure.
No, but that means already bipartite.
Yeah,
But chirality doesn't meet bipartites.
I don't know.
So essentially, if you have a unitary operator, which gives you an anti-symmetry for your Hamiltonian, so u times h times u to the minus 1 equals minus h, then that is called a chiral Hamiltonian.
Nice.
Then eigenstates must usually come in pairs, plus minus energy E. And then you can now argue if you have a translation invariant Hamiltonian and you have a unit cell which consists of an odd number of sides, then there must be a flat band at the chiral energy equals 0. Because it's not saturated, there's no counterpartner to that. So you must have macroscopic degeneracy at equals 0, which means you have a flat.
Yes.
Right? And so this is as concerning flat bands, chiral flat bands. So like here, you have 3 sides per unit cell. So you don't have to even further. You can, okay, you know this is chiral, actually it's even bipartite, but then you can conclude immediately that there must be a flat band at energy 0. You don't do any other calculations. That's it. Whatever your hoppings are, e to the I phi doesn't matter. But in general, if you have Hamiltonian, which has an anti-symmetry using a unitary operator, then this is called chiral symmetry. And a consequence of that is that there should be, maybe there must be a specific basis. So you can now transform your basis into a very specific one, which will be bipartite. But you must not use this bipartite basis and still.
Yes.
So, for instance, SSH is bipartite. Even the simple one-dimensional tight binding chain is bipartite, and therefore chiral. But they don't have flat bands because SSH has 2 sides per unit cell, and tight binding has even just only one, so it only has one state at the chiral.
It's not related with the particle symmetry.
It is related if you dwell a bit more. Yeah. So it can be related. It must not.
If U is the particle transformation, then the Hamiltonian will transform to the minus h.
So it is related.
Nice.
But you can have a chiral a chiral Hamiltonian which is not particle hole symmetric.
Yeah.
But it can. Or maybe the other way around, if it's particle hole, then it's always chiral. I'm not sure.
So now just the last part of this discussion, non-orthogonal CLS. We start with the same diamond lattice. And what we do is we break chirality. We introduce these hoppings. And then we thread a flux through this. By doing that, we introduce basically complex hoppings on all these sides, all these bonds. And by doing that, breaking the chirality also shows that.
Sorry, why complex phase emerged at this top and the bottom bonds? Because you introduce flux within these diamonds?
Sorry?
My question is that you have this structure now and you introduce the flux inside these diamonds.
Yes.
Right?
Yes.
But then you also do something, and then you have hoppings which are I think complex on the top on the horizontal bonds also.
Yeah.
Why it happened? My question is, you did because there is some another, should be some other operation which did it.
So let's go step by step. So let's start to top left. This is the good old diamond shape.
Yes.
Good. Now, next step, we go to the right. What do you do? You add hoppings.
Yes.
Okay.
You
just add.
Which are real?
Yes.
No, still real.
Add hopping. Let's say real, right? Let's for the time being say they are real. You break chirality, by the way.
Yeah.
And you break also the bipartites.
Yes.
Okay. Now you go down. What do you do then? What's the operation?
We basically introduce complex hoppings on these wedges.
You add complex hoppings. You make some of the hoppings complex.
And basically that is saying that, okay, there is.
Yeah, but you will also get a flux in these little triangles then, right?
Yes.
Yeah, but
yes.
you didn't.
I didn't show
you just
it.
don't say that. Okay, is that clear, Oleg?
And now
So,
we are
and now the last step. Now we go to the left and you make more hoppings complex, or what do you do there?
So basically, I mean, okay, this is a diagrammatic error. The thing is that when I'm making this complex, I'm also making these ones complex.
All right.
I didn't show it, right?
Yeah, I didn't show it.
Okay, so it's just two sub steps. So you basically could just go from top right to bottom left.
Yeah.
Okay.
This was not necessary.
So okay, so you make
Sorry.
Now the puzzle was solved.
So that you don't have flux in the upper triangles and lower.
No,
Is that the goal?
we see that we'll have flux in upper triangles, lower triangles, and everywhere.
Just everywhere, okay.
See, the thing is that we had basically breaking the chirality and all this. The flat band energy shifted from 0 to -2, and the dispersive bands all went to one side. And basically, this is the overall current thing. The funny thing is, and I mean, I'm sorry for this diagram, because we are threading hopping over here, over here, over here, over here. So we are basically introducing a total non-zero kind of flux over the entire loop. So if you consider this loop, the larger one, then we are introducing a non-zero flux in that loop, and that can be seen from this diagram. So basically, here we have 4 sine 2 phi for flux that we are getting. So for each of them, and then a current, and then we have this on the other direction rotating 6 sine 2 phi kind of thing. So if you add them up, you get a non-zero current throughout the entire structure.
which means supported by the CLS.
Yes, and which is supported by the CLS, this entire whole CLS.
But just to be sure, so do you have some global current on these edges, top edge and bottom edge? which is flowing maybe to the left.
You will not get local current.
You see, the whole point is that we know that there are flat bands which support compact localized states. Something compact,
Yes.
And
not extended.
these compact
Now-
localized states.
Now
are
you want to
symmetric
have a
current.
compact state which supports also a compact
Current.
vertex. I wanted to call it vertex, they don't want it current or whatever, something
Well,
which is
it's okay, yeah.
local and flux or whatever, you know, something which is compact and local. You can excite it and it sits there. So that's what the whole talk is about.
We have actually, I have tried in some other scenarios
You
where I
have
had like CLS lined up and then I tried to do a cut and to see that if there is some kind of current.
I mean, you can always excite some Bloch states,
Yeah.
some extended states, and then ask whether there will be some currents flowing, you know, you can do that, but that is not the goal here. The goal here is to come up with models which have flat bands, compact localized states, and compact currents, ring currents or whatever you call them. Compact.
So in this case, for example, the current is throughout. This is the non-zero current overall, which can be broken into these domains.
Okay.
Can you explain for standard diamond chain?
Yeah.
There is no flux.
There is no current.
No current.
Yeah.
Can you show again? Yeah, this one. No,
Yes.
no, this one.
Yes. You can imagine that there is a 2-phi flux being threaded through this. Because
Because it's for any kind of phi and any kind of distribution, it's some law you cannot produce.
No. Again, look, one thing is when you say you have a plaquette and you count, and you say there is maybe some synthetic magnetic field,
Yes.
blah, blah, there's a flux, that's one thing. The other thing is now you excite something, and you ask whether this excited something produces some kind of current. And we specifically want to excite compact localized states and ask whether they can produce currents. And the answer is no in this case, because it's a bipartite structure and the CLS lives only on the majority sides by definition, by construction. So whatever you do, you can. Why? Because to get a current now with the CLS, you have to not just compute the phases of the hoppings, but you have to multiply them with the amplitudes. And there's always a zero amplitude on a connecting side because it's a bipartite.
So basically, this is the summary. We can construct all band flat bands with broken time reversal symmetry systematically. By, like I said, that we need like an enclosed kind of plaquette where we start the threading of flux with, and possibly with appendices if you do not want your life to be very complicated. Then this construction basically involves local unitary operations, which can be selected from the appropriate group of operation. And this group of operation depends on either on the dimension or the number of neighbors that each of them have. These currents within these plaquettes are localized and they depend directly on the flux value, which we saw in the case of all band flat or in the case of this general flat band scenario also. And that's basically the last one.
What if you have singular flat band?
Singular flat band.
You will have some global current if you will do the same manipulation.
So again, the question is if you have something, you can get anything. So let's say you have a singular flat band which supports a compact localized state.
Yeah, but
Then the question is, can a compact localized state support a compact current? That's the question.
okay, and
Probably your
it
question.
can
And
provide.
I don't know the answer. Probably yes, but
We did not prove.
that's
Maybe, I mean, it depends, right? I think if you take the entire loop of that spreaded compact local state for this singular flat band, you can have some current.
Yeah, correct. I confused the non-orthogonal CLS include the singular. Singular flatband is a part of non-orthogonal CLS.
It is an endpoint. Yeah, okay. It's well, singular is singular, and non-orthogonal means here linearly independent. So in a sense, it's different. But I think in the can you show again the results for the So I don't think this is a systematic study here. So what this shows is that you can construct also time reversal broken flatbands with compact localized states supporting local ring currents, compact local ring currents, for linearly independent flatbands. That is, those which are not orthogonal, but they are not singular. So maybe you can also do this for singular flatbands, but this is an example. This is not saying that for any non-orthogonal you can do it. Probably yet we don't know, but it's just examples that you can. And maybe you can also for singular ones. Why not?
Yeah, I don't see why not. I mean, maybe we have to sit down and do a calculation and see. But that's it.
More questions? No one? We had a lot of questions.
Good. Then let's thank the speaker again. Thank you. And there should be some food on.
Yes, should be.
Today we even got
Who will be the first to check?
Thank you.